Welcome to electromagnetic spectrum. Simply, electromagnetic spectrum is just simply all the different wavelengths of light. For example, if we look over here at the chart on the right-hand side, up here we have gamma rays. That is a type of light and has a certain wavelength. Down here are radio waves, and there's a little tiny band in the middle here that are what we see visibly, and they've kind of blown it up so that we can see the colors of the rainbow. But there's some simple characteristics of all waves that we have to consider. Number one, they all travel at the same speed, so they all have the same velocity. And if we look at this, the speed of light is 3.00 times 10 to the 8th meters per second. Now, we want to pay really close attention to the units in this particular case, because as we start to do problems, we're going to have to consider those units. Wavelength. If you look at the two waves down here at the bottom, if we go from crest to crest, that would be a wavelength. And if we go from crest here to crest here, that would be a wavelength of the smaller wave. We could also go from trough to trough or from center point to center point along the line of symmetry. But the wavelength is obviously how long it is in meters. And that wavelength is always symbolized by a lambda. And so this distance in here is symbolized by the letter, and it's a Greek letter lambda. And it's a small case. Now, frequency is the other factor that we have to consider when we deal with waves. And frequency is the number of waves per second that travel by us. And so, again, if we look at wavelength, that should be in meters or some version of length. And frequency is actually going to be in waves per second. So, in other words, the per time. And waves per second is also equal to the unit that we know as hertz. And so if I write up here Hz, that's what that is. And the equation that we're observing down here says that the speed of light, c, is equal to the wavelength times the frequency. What we see here is we see these two different waves, and one has a very long wavelength and one's got a very short wavelength. And what's going to happen is they're both traveling by us at the exact same speed. And so if you have a very short wave, then you'll have lots and lots of frequency. In other words, it'll happen over and over again very quickly. If you have a long wave, it's going to happen. It's going to be short, or the frequency is going to be smaller. So what we're going to do is on the next page, we're going to start looking at, well, what if we know the wavelength? How would we find the frequency? And that's what this little equation is here, is to convert between them. And really, if you think about it, this equation is simply an equation that you've seen lots in math, y equals mx. And so we'll know one of these factors, and then we can solve for the other one. So let's go on to that. So if we look at our question here, if we have red light with a wavelength of 700 nanometers, what is the frequency? In other words, how often does it pass us? And so the 700 nanometers are really, 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 really small. In fact, I know the conversion for this, and you guys will soon know the conversion too, but 1 meter is equal to 1.00 times 10 to the 9th nanometer. So there's lots and lots of nanometers in 1 meter. So remember that c, the speed of light, is 3.00 times 10 to the 8th meters per second. So our wavelength has to be in meters also. We can't just leave it in nanometers. So what we have to do is convert that. So what we'll do is we'll start out with our 700 nanometers. And we set this up and get rid of nanometers. So nanometers are going to go on the bottom, and we're going to basically cancel them out mathematically. So this is going to be 1 times 10 to the 9th, and this is going to be 1 meter. And so if we convert this, and we're not going to worry about we're going to do this simple, and then we'll convert it to proper scientific notation. But this is going to come out to 700.0 times 10 to the negative 9th meters, which, if we move our decimal, we should get 7.000 times 10 to the negative 7th meters. Okay, now that we have our wavelength in the proper unit, now we're going to move on and we're going to see if we can convert this into frequency. So if we scroll down a little, get a little room to work, I have the speed of light, 3.00 times 10 to the 8th meters per second, is equal to the wavelength, which we just figured out in meters, 10 to the negative 7th meters, times the frequency. Now remember that this little symbol there is nu. It's the Greek letter. It kind of looks like a little V. Now we need to solve this, and so simple math is getting away from this variable. And so I'm going to take my 3.00 times 10 to the 8th meters per second, and I'm going to divide that by, I'll jump this up, 7.00 times 10 to the negative 7th meters, and that should give us our frequency. Now, if we pull up a calculator just real quick to see what we get here. So we do our calculation. 3, and this double E is the same thing as times 10, so 3E8 divided by 7E negative 7, and what we come up with is 4.29 times 10 to the minus 14th. So we get 4.29 times 10 to the minus 14th. Oh, actually positive 14, I'm sorry, positive 14th per second. So basically that means we have 4.29 times 10 to the 14th waves every second go by us. Okay? And so the calculation is just simply trying to get from, the speed of light. If you're given frequency, you should be able to calculate wavelength. If you're given wavelength, you should be able to calculate frequency. Now, one of the things that we discovered about waves is they have energy and wavelengths of light. And the way that we did that is through the photoelectric effect. And what the photoelectric effect, what they figured out was basically if we shine light on a metal, it will actually, and it has to be a certain frequency of light, it will actually kick off electrons, and those electrons will bounce off, and we can measure those electrons as they're given off. And so you'll see here in this first picture, we have the wavelengths of light coming in here. They're coming in and they're hitting this surface, and as they hit the surface, these electrons get punched off of that metal. Now the second picture is what we're seeing is the light coming down hits, and if the light didn't have enough energy, the electrons bounce back and are recaptured by the plate that they were leaving. This final setup shows as light comes in and hits this plate, if electrons will jump to another location, we actually create a circuit and we can measure the electricity flowing through a circuit. And that electricity equates to energy, and that energy could be calculated by the frequency of light that is actually being absorbed by this plate. So the equation that we have up here, E equals H nu, and that's frequency. It should be a little nu symbol instead of a V and look a little better. But the energy of light is equal to this constant, this is called Planck's constant, times the frequency of the light. And so if we know the frequency of light, we can calculate how much energy that light is actually giving off by simply putting in the frequency. Now, because we know the energy of light by what we just looked at with that equation, we figured out that with different gases, we got this thing called an emission spectrum. And what an emission spectrum is, and an absorption spectrum, is if we shine a full spectrum light through gases, it'll absorb certain frequencies of light, and those frequencies of light are the ones that ID that particular gas. Down here, if we excite the electron or excite the atom, these are the specific frequencies of light that are being given off. In other words, it gives a fingerprint for the gas we are playing with. If we calculate the energy right here, we can actually calculate E equals H nu, calculate the frequency, calculate the energy, and we know how much energy required to give us this blue light. So we can relate this to what's going on with an electron inside the atom. We'll go further with this on the next video where we start to explore what each one of these lines means. So we'll come back with the next video and explore what the emission spectrum tells us.